Hello and welcome. Today I'll be describing, in simple terms, the dual nature of matter as a particle and as a wave. And I will also discuss the double slit experiment. So in a previous video I talked about this French physicist de Broglie, and he came up with the equation that the momentum of either a photon or an electron is equal to some constant called Planck's constant divided by the wavelength. And in that way he thought that matter, such as electrons, can possess wave-like properties, and that's why they have a wavelength. So H here is Planck's constant. I think there might be a C there. Lambda is the wavelength. And P is equal to the momentum, which is also equal to m times v, or the mass times the velocity. So it was being figured out around the 1920s that matter is sometimes behaving like a wave. And mostly the credit is given to the double slit experiment that reveals the wave-like properties of matter. So let's imagine you have a ball of matter that emits beta radiation. Well, beta radiation is just electrons. So we have a ball of matter here. Let's not focus about what's inside, but we got electrons coming out in pretty much random directions. Well, we're going to focus the beam of electrons through a single slit, okay? So we have a directional sort of stream of electrons. And what we're going to do with that stream of electrons is pass it through two slits, okay? And we're going to have a wall on the back here. So these are two slits here. Same size opening. We have electron beam coming out of here, two slits here, and the electrons are going to hit back here, right? And imagine we have a detector that can detect the electrons. Each one of these squares are a detector. So if we get one electron hitting here, we'll hear a click, say. Or if we have an electron hit over here, we'll have a click. But you wouldn't expect, to hear clicks if you just shoot one you wouldn't expect to hear two clicks at once if you just shoot one electron. Well, to make this easier and less painful on your brain at first, let's think of what we would expect to happen for bullets and what we would expect to happen for water waves. So if we have a gun that's shooting bullets, this is our gun, right? And it's shooting bullets. Okay? And we're shooting these bullets through two slits. Imagine it's a machine gun and you can rotate the gun, so you can either shoot through that slit or that slit. Okay? So the gun rotates. It's like a machine gun on a bipod. And imagine you still have the back wall back here, and you have the same sort of, imagine a sandbox that catches the bullets, and then you count the bullets out of the sandbox. So you expect the bullets are going to come through here, and they can ricochet off the sides. So most of the bullets, they're going to come out this way and hit about here. Sometimes they're going to ricochet, a couple of them going to hit here, maybe ricochet off that, hit up there. Similarly, if the bullet actually goes through this hole, you'll have a lot of them go there, a little bit of them go there, a little bit of them go there. Okay? So now if we graph the number of bullets that are in each sandbox, right? So let's say we count 5 bullets here, and 1 bullet here, 1 bullet here, 5 bullets here, 1 bullet here, 1 bullet there. Okay? So we graph that, we're going to get something like this. Right? No bullets are, there's no way a bullet's going to bend around this corner and hit the middle of the wall. Okay, even though I drew something there. I mean, it's not going to hit the middle of the wall because a bullet is a particle. It cannot bend around a wall. So, like, I drew this graph sideways here. So this axis here is number of bullets, and this axis here is, well, it's the position on the wall where the bullet hit. Call it X. So you have the most bullets where you would expect the most bullets, and where you wouldn't expect any, you don't have any. Now let's do the same experiment with, say, water waves. So imagine we got a buoy, and we're producing waves in water, and that water is going through 2 slits. Okay? Well, imagine you're doing the buoy up and down out of the page, and the waves are going this way. Okay? Well, if you know a little bit about waves, you know that waves interfere constructively and destructively. And I don't want to get into too much detail here, but you're going to get, say, constructive interference here, and then destructive here maybe, and then it's going to be a little bit constructive here, destructive, and then a little bit constructive, and then you're, going to start going the other way. So your graph is, I'll redraw it to make it clearer. Okay, so this is our back wall. Now we're going to draw our graph over here. Okay, so you're going to get, what we're imagining is the height of the wave at that point. So this axis would be height of wave. Okay, so when you get constructive interference, you're going to get a really high wave. Destructive, it's not going to be very high. But then there's going to be some constructive, and it's going to alternate like that. Well, okay, it's the middle is going to be actually really constructive. So the middle one's going to be the highest peak. And you're going to get less and less and less. So that's how waves behave. Whether it be, well, a light wave, or water wave, or sound wave, things of that nature. Now we do the same thing with electrons like we were doing up here. Let's redraw it. So we have our ball emitting electrons. There's a beam of electrons. It's going through 2 slits, and it's hitting the back wall. Okay, so imagine our detector that detects the electrons. I talked about the photoelectric effect in a previous video. Never mind, disregard what I just said. But imagine the electrons can hit a detector like a piece of metal and knock off other electrons. Like, say, 1 electron knocks free 2 electrons. Then those 2 electrons will do 2 more electrons, so you have 4. And those 4 will issue 2 more, so you have 8. And so on and so forth. You can amplify the number of electrons you have to an electrical current, and in that way you can have a detector. But those are just minor details which you don't have to think about if you don't want to. But this is a detector that can detect electrons, where the electron hits. Now, so we're shooting electrons through these 2 slits. What do we see? Well, we see the same as we've seen with this wave pattern, right? Well, believe it or not, that is what we see. It doesn't matter if you do believe it or don't. You're going to see, total constructive interference, and then it fades away as we go away. Well, now, how does that make sense? Because I thought electrons were particles. Well, they can actually sort of behave as waves. Let's imagine we close off this slit, right? What's your pattern going to be? Well, your pattern's going to look like that. Similarly, if you close off the other one, you're going to get a pattern that looks like that. Well, you'd expect you to add those together and get that, but you don't. You add those together, you're going to get this same thing we got with bullets. But that's not what happens. So what's going on here? Well, nobody really knows what's going on. But what can be said is that, well, the electron's sort of acting like a wave. It's going through both of the slits. It's constructively interfering at some points. This point, for example, is destructively interfering at others, so on and so forth. But then when you close one of the slits, well, now all of a sudden it's acting like a particle. Well, what's up with that? Well, no one really knows what's up with that. It's just the way things are, the way it works. You perform the experiment, that's what you get. So that's a little about the dual nature of matter as a particle and as wave. I hope you found that helpful, and have a good day.